It's a pleasure to be here. So I'm going to speak about explainable AI, but first let me give some background. I'm the head of the Deep Learning Lab at Tel Aviv University, and we try to be as diverse as possible with regards to the projects that we are running. So as Jacob said, projects in computer vision, such as this system for real-time video segmentation. And as part of the interdisciplinary cyber center, we have a lot of projects at the intersection between AI and cyber. And we also venture into engineering, designing antennas for mobile devices, and a little bit into quantum computing and for the best schedule for quantum hardware, and also into medicine and neuroscience. So as AI is moving into all of these disciplines, there's a question, how can we interpret what AI is doing? So this is especially a concern given that AI now plays a role in finance, insurance, medicine, and so on. We need to understand what AI is doing. Otherwise, how can we trust AI when it decides to hire someone or not hire them, whether to give them credit or not give them credit? When AI is making decisions about healthcare reimbursement, does it suffer from a racial bias and so on? And finally, how can you trust an AI to decide about your academic future? So all of these call for explainability, and I'm going to describe how we achieve explainability and how we can use explainability in order to trust the AI machines. So I'm going to start with a very simple method for explainability that is generic. You can apply it to any classifier that you have. You don't need to go into the black box, you can just use it. So we start with an image I, and we have a pre-trained classifier F. And F tells us whether this is a dog, a cat, a bird, what kind of species, and so on. We would like to understand what is F actually looking at in the image. So we cannot dig into F. F is a black box. What we do, we train a second network, network G. This network G gets as input an image and outputs a weight map. This weight map basically tells us what is important in the image and what is not important in this image. And once we get the heat map, we need to actually tie it back to the classifier. So what we do is we look at the image. This is a multiplication of the original image and the weight map. And we get the image over here. We get this image. Now, in order to train G, we need to get a signal back from F. So what we do is we add a constraint that once we multiply the image and then pass it through F, it should have the same classification as the original image. So we know that the classifier attends to the heat map of G if F on this image is the same as F on this image. This is actually a very effective constraint. The only issue is that if we take the entire image as white, then classification would be the same. So what we do is to add a regularization term that basically tells this image to be as compact as possible. So this is a very generic method. We apply it in images, we apply it in bioinformatics, works great. I'm not going to go through the results. I'm just going to say that this is state of the art in what is called fine-grained weakly supervised detection and segmentation. So the first method looks at the classifier as a black box. Let's move to another method that actually looks inside the way that the classifier works, look at the activations inside, tries to understand from the activations what is going on. And I'm going to talk about these kind of methods in the context of transformers. Transformers are basically the most powerful model that currently exists. It's behind the revolution in natural language processing since 2017. And in the recent years, also in computer vision and in other domains such as graph data and so on. A transformer is this elaborate structure that would take about 50 minutes to get into, but let me just say that it has an encoder, it has a decoder, it has attention layers, it has projections, normalization layers, and so on. And what Lior and Lior did is to come up with a way to look at all the activations that are going on over here and understand how does the transformer look at a specific input. So the input can be a text or can be an image. In the case of computer vision, we take the image and we divide it into patches, and then these patches become what we call a token. So in natural language processing, a token is just a word. In graph, a token is a node. In images, a token is a patch. The method that we developed for explainability is generic, works in all cases. So the main characteristic of transformer is having an attention map. So each one of the tokens attends to each of the other tokens. And there's a special token called CLS. This is the most important token since we extract the classification from this specific token. So earlier work said, well, if we just look at the attention to CLS from CLS to each one of the tokens, then you can tell which token is more important than others. But this is a very myopic view. It ignores the other layers. Just look at the last attention layer. It doesn't look at multiple attention heads, doesn't look at any other part of the transformer, such as the projections or the normalization layers. So what Lior and Lior did is to combine the attention information with the gradient information. In neural networks, the gradient of the network is a very strong signal as to what is important. It's actually the signal that we use during training. It tells us how much the outcome changes when we change the input. So Lior and Lior combined the attention together with the gradients, and we're able to come up with a very elegant solution that combines everything in one unified way. And what they get is the kind of the attention maps that you see over here. So if this is the input image, it has a dog and a cat, and we have to classify what is in the image. For the label dog, our method highlights the dog. For a label cat, it highlights the cat. Other methods either have the same explainability map for both objects or are very partial in their outcome. This works for images, it works for text as well. So what you can see here is sentiment analysis. We get text, we need to say whether the sentiment is positive or negative. When we say explain how you got to a positive label, we see that the positive words are highlighted. If we say how we got to a negative sentiment, then we get the negative words as the ones that have been highlighted. So sentiment analysis is perhaps the simplest task in NLP, but actually works for any task that transformers work and are very effective at. So consider this task that combines images and text together. So we have an input image, and there is the question, did he catch the ball? The answer given by the transformer network, by model transformer that combines text and image, is yes. But how can we know how the computer got to the conclusion? Maybe there is a bias toward the answer yes. Maybe just guessing. The explainability method highlights the relevant part of the image and the relevant part of the sentence that got us into this conclusion, and therefore we can trust it much more. So we talked about two different methods of obtaining explainability. The second method that we just described is actually very well adopted, although it's very recent, by many other researchers in computer vision and NLP, and it's become the standard for transformer explainability. But I would like to shift our attention to zero-shot learning. Zero-shot learning is perhaps the hottest topic in machine learning, truly revolutionary, and in 2 slides you are going to know how it is performed. So this is entirely something that is cool, but yet very accessible and easy to understand. The powerhouse for zero-shot learning in computer vision is a network called CLIP. This is by OpenAI, very powerful network. It was trained on 400 million images together with their captions. So you basically go on the internet, you look for images and the sentence that describes the images. And then you build this huge matrix that for every image matches it with a sentence. And you build a machine that, given an image and a sentence, gives you a score. If the score is low, the image does not match the sentence. If the score is high, the image and the sentence match each other. The sentence describes the image. So how can you use it to perform new tasks? The simplest way is for classification. There's an image over here, you want to know what's inside the image. So you prepare a template, a photo of some object. So is it a photo of a plane, a photo of a car, a photo of a dog? You get multiple sentences over here. And CLIP basically selects the correct sentence. And then you get classification. This is a photo of a dog. So this is pretty amazing because CLIP was not trained to do this task, but yes, we're able to do it through the power of zero-shot learning. Now, we want to understand what's going on inside of CLIP. We want to go inside and read what is CLIP thinking. Now, CLIP can match sentences, but it cannot generate sentences. So this is a work by Yoad Yoav that basically combined a language model. A language model is a model that, given a sentence or a part of a sentence, always generates the next word in the sentence. And it was combined together with CLIP in order to generate sentences that match the image. This is done in a very elegant way. I'm not going to get into the details of without any training. This is only done at inference time, and therefore you don't have the biases that come with the fine-tuning or with the training. And you apply it, for example, to this image, and you see that if you look at other systems, what you get is a very formalistic type of description of the image. But if you apply this method, you get something that is very descriptive, and it really behaves like a human, describes the context. It actually has a lot of world knowledge. It can identify things. So given this image, we get the Simpsons as the answer and so on. And it's very chatty. It describes whatever it sees in the room, not just a short description like other methods. It gives you a full description of what is going on. And this is done for many examples. I'm not going to go over them, but it's a unique feature that it describes in a way that humans would describe without skipping all the details. And even though it was never trained on OCR, for example, it can read. So basically it says, this is Shin's truck cake. Never saw this image, was never trained to read, but it can do it. And it can do other cool things. For example, it can do arithmetic with meanings. So this is a trick that in natural language processing they did for a while, but now we can do it for computer vision. So look at this puzzle and let us know what you think this is. So this is kind of a weird equation. It takes time getting used to, but let's start with simple. What is this? You take a king, you subtract a man. What you get royalty. You add royalty to this young woman, and what you get is a young queen. So basically we give these three images to CLIP, and then we use our method to extract this text. And we know what's going on inside of the meaning space, the semantic embedding that CLIP employs. And I will let you guess what's this one. You take an egg, you subtract a chicken, some sort of food from an animal, you add a cow, and what you get is a cow's milk. And it's pretty cool if you take these many basketballs and you subtract one basketball. So the property of basketball you remove. What you get a bunch. Makes a lot of sense. Also works for addition, and also works for relations and analogies. So if you would like to solve questions such as A is to B, such as C is to D, this is actually the right equation to solve it, because if we take this equation, C plus B minus A, it's the same as A minus B equals C minus D. We give these three images to clip with the correct arithmetic operators, and then we use our system to extract the text, and we get Egypt. And this works marvelously. It displays a lot of real-world knowledge, and so on. So we describe three different methods for explainability. One is black box, one is activations, one is actually making the AI speak. Let's speak about some applications. In a recent work by Ronnie and Ilah, they were able to use explainability not just to show humans what the AI is thinking, but also to help AI. So the problem with AI, just like many of us, is that it chooses the path of least resistance. So this is a very powerful method called style clip for modifying images based on the text. But when you ask it, a person with a purple hair, well, it never saw many men with purple hair. So it basically leaves the input image untouched. The attention mechanism attends to everything, doesn't make any emphasis on purple, and the attention for the image, the red parts, doesn't look at the relevant hair part at all. With our method, we prevent this neglect, and then we make the system focus on the hair, on the purple part, on the actual hair, and it is able to create the image with the purple hair. And this also works for zero-shot learning and one-shot learning, really improving the accuracy across multiple data sets based on the fact that it doesn't neglect any part of the sentence. And let me just share one more result that we got. This is a collaboration with the Technion that looks at classification and tries to think like a scientist. Let's say you go to a scientist, a zoologist in this case, and ask them, what is this image? And you get the bird species. And then you ask them, why do you say that this is this specific species? Well, they can either say, well, I'm the expert, and you should believe me, this is the AI method, the black box method. Or they can say, well, it has this crest, the shape of the beak is pointed, the tail is long, the chest is red, and so on. We would like the computer to look at the classification task, basically just given images and the classification, and be able to come with the important features, which we call mid-level features, not about pixels, not about the species, it's about the characteristics of each one of the birds that we can use to describe what is going on. And if the computer is able to come up with the color of the feathers, the shape of the head, and so on, then we can know that we can trust it, and we can discuss with the computer the reasoning behind the decision. The way that this is done is by combining neural network with decision trees, because decision trees give us very simple rules, and then we are able to benefit from both worlds. And at the junctions of this decision tree, we get these features, that the mid-level features that we would like to get. So thank you very much. I really enjoyed this talk and looking forward to questions. We discussed three different methods for explainability: a black box one, a heat map, and one that actually converts the input of the inner workings of the classifier to text. And then we describe how to use explainability to improve algorithms and how to make the computer think like a scientist. Thank you very much.
Thank you very much, Professor Wolf. Amazing presentation. We have a few questions for you. The first question is about, did you try this explainable AI, marvelous technologies in the healthcare industry? Can you elaborate more about that in the healthcare use cases?
Yes, so this is a great question, thank you. So if you can remember, when we started the talk, I was talking about a work that is done on COVID-19 classification from CT images. I just showed one slide. Let me try to find it. So this is actually using explainability, this work. It uses explainability in order to learn a very powerful embedding. So we would like, for example, have different patches that have high explainability score, have similar embedding. And we also go by explainability can point to some artifacts. So in some cases, the classification of what we see in the CT scan really focuses on very localized places that might mislead the classifier. So we use the explainability score, find out where the system is attending, remove this part, and look again. And we actually create multiple versions at test time from the image in which we make it ignore the most prominent parts, and then we create some sort of rerouting. So this is one application where we use explainability in medicine. The method that I was talking about earlier about black box with the network G that creates a wet map, we're using in bioinformatics, and are able to show that we can learn the specific role of genes in the specific context, work that I like very much, unpublished yet. And we can use it also in other places in healthcare and biology.
Wow, amazing. We have additional questions, Professor Wolf. Did you try this technology on speech? And I'm combining another question, which is very similar, related to video. Okay,
so with regards to speech, there is an ongoing work that we are trying to think, how would explainability look in speech? In the sense that in images, you get a heat map. In speech, how would you hear a heat map? It's not something that is easy to think out the perceptual would work. So what we try to do in speech is to actually use explainability in order to emphasize some parts of the audio and de-emphasize other parts and then listen to it. So let's say that there is something that I'm saying that is not clear. The classifier that tries to transcribe what I'm saying is confused. We would like to understand why it's confused, basically reinforcing the parts that I'm mispronouncing, weakening other parts, and maybe then go in the other direction, not just understand why the classifier is confused, maybe also fix it. Go and correct the parts that confuse the classifier. So this is an ongoing work. I cannot share more than this, but this is indeed a very important question because it's not as easy as it is in computer vision, NLP, and other domains.
And the last question, can one use explainability method in order to increase fairness?
So I was talking about fairness as something that explainability would lead to. But if you look at the literature, it's actually two different disciplines. The work that we are trying to do right now is indeed to combine the two, because it makes a lot of sense that if you know what you're attending to, then you can say whether the classifier has some bias against protected groups and so on. So this is indeed something that we are trying to do. It's surprising that it's not being done that often, but fairness is not an easy topic. Just not looking at the protected classification doesn't mean that you don't look at other things that are correlated with it. So fairness is something that we are actively working on. I have a submission that I didn't get into. It's not as simple because there are many intricate points that you need to take into account, but it's well worth doing.